My name is Dong-hee Kim. I'm technical application scientist in cheminformatics team at Merck KGaA. I'm very excited to discuss lateral synthesis software Cynthia today. You will know how Cynthia came into the significant advance throughout its development. It's able to design viable pathway for complex molecules that has been validated at bench. But before we discuss Cynthia in depth, I'd like to talk about history of lateral synthesis before current generation of lateral synthesis tool on the market. You know, there are not really an art, but highly trained skill to lateral synthetic design of target molecules. It takes many years of training and schooling to be proficient for pathway design. So the thought of teaching computer has not been a trivial task. And this idea has not come recently. The chemists start to approach this idea and problem more than 50 years ago. So it started in 1963, the very first proposal lateral synthesis software that enabled a database access to navigate backward and connect to target to readily available precursors. There was seminal paper from E.J. Corey in 1967 and outlining lateral synthetic rules for systematic pathway design, proposing these rules by computer. In 1969, we saw very first attempt at software which Corey and VP creating the organic chemical simulation of synthesis. And Corey began pursuing his own tool, what became known as LASA. LASA was able to suggest specific reaction for target. The task of choosing the right synthetic move were left to end users, making it semi-automatic framework. However, there was lack of experimental effort or validation, and the most notable document, validation of synthesis, failed in just first step. From 1970s and to early 2000s, many groups began pursuing the computer assistant approach to lateral synthetic planning. However, no clear success was achieved. And it was believed that the better computing power are required to navigate, such as combinatorial explosion of possibility. But that wasn't yet possible. In early 2000s, with the success of IBM, Deep Blue, the power of computer drastically increasing, there begin to be renewed interest. Since then, we have seen a steady growth in the area of machine learning, AI, and in silico lateral synthetic planning tool. One of that was Chematica, and today is Cynthia. With the success of Deep Blue in the rise of the machine, the Professor Bartos, who is creator of Cynthia, began equating the problem that IBM with chess with lateral synthetic planning, and his idea for new breed of computer-assisted lateral synthesis design software. After all, it was only solving for the problem of searching enormous tree and network of possibility. The first question was how to represent chemical reaction and molecule with different type of representation that could have been chosen. The first argument for using the network representation was ease of visual inspection, which is also why it is used in wide range of application. For example, maps for biology. Secondly, even more important reason was that for searching for connection over network is computationally more efficient than searching connection over list. The difference became even more significant with the increase of the size of dataset and synthetic planning. We all know that there are very large datasets that are cleared for multi-step connection between the target and available substrate. Therefore, so-called bipartite network representation was chosen. There are two types of node. One denotes the substrate and product molecules, and another denotes the reaction operation. With the use of this representation, the network of published reaction, called it the network of organic chemistry, was created. The vast network contained on the order of 10 million substances in similar number of reactions connecting them. So with the best representation chosen, a set of algorithms were created to be able to traverse this new network of organic chemistry. The algorithm can search rapidly the large network of public reaction with user-specified criteria and constraint known as scoring function during the search. And in 2012, this new complexity were added into the program. So new construct pathway for published molecule that commercially available or known building block actually quantify them based on the user's constraint. The goal has always been develop a program that was able to develop novel pathway for target, whether known or unknown in the literature. So next step in journey was a problem of retrosynthesis in teaching computer how to find the pathway for these molecules, which turned out to be much more complicated than simply just connecting the published reaction into network. In the problem of retrosynthesis, the first thing to do is teaching the computer the rules of organic chemistry, and generalization of literature precedent to reaction was crucial. If we wanted the program not only generate synthetic molecule, but also for those that were never synthesized before, for example, recently isolated natural product or even novel drug candidate. To accomplish this, there were two options available at that time, and one is machine extraction, and another is hand-coded reaction rule database of Cynthia. Unfortunately, the machine extraction from the literature, it's not possible to know how the reaction core should be or how to accurately select incompatible functional group. However, all of this information is crucial, and if we would like to have the software to propose chemically correct synthetic pathway, the solution is definitely expert hand-coded rule database of Cynthia. So I'd like to give the very quick example of one of the example of the machine extraction rules. Actually, it is P4 of it. Here is example, and it's stereo selective alkylation reaction, and the core is the core of the rules is colored in orange and specify the atom changing their environment, and also include the flanking atom up to 3 bonds away from that reaction center. So nevertheless, even with the extended neighborhood, this rule doesn't actually capture influence of the stereodirecting methoxy group information. So of course, it's possible to extend the number of atoms included in this rule. However, this would make all simple transformation over specialized by that applicable only to specifically designed skeleton. So without inspection by human expert, defining the proper route is actually not possible. So when you look at potential pathway on the bottom, if applied on the right circumstance, you do get successful outcome like example A. How about look at example B? You can also have inappropriately proposed alkylation in presence of incompatible groups such as this nitro group creating acidic proton on the basic condition LDA. So finally, this proposed pathway will not go as planned. How about example C? So because of the absence of the distance stereodirecting methoxy group, your final product is racemic mixtures with the incorrect stereochemistry. So for this reason, our expert team began hand-coding the reaction rule based on published reaction so that program could recognize this required critical context. Our team of expert chemists began teaching this program chemistry by hand-coding reaction rules into database. Each rule is based on reaction mechanism and take into consideration stereo and regiochemistry, and even admissible substituent in their electronic and static effect. So all rules also include additional information such as functional groups that need to be protected or which group could be incompatible with the reaction condition. So during coding of each rules, the chemists have to actually consider the reaction mechanism as well as reaction condition when selecting and identifying any possible incompatible functional group that could prohibit reaction from proceeding. So once the rule were well on the way, the next step was teaching software various types of chemical logic in order to enable it to find pathway for target molecules. In addition to incompatibility and protection, additional logic has also been built into the software that algorithm may identify other issues as well. For example, the reaction that are non-selective. So in the situation where the same reaction can be applied at multiple places within a molecule, leading to undesired mixture of a product. The algorithm are able to detect non-selective reaction during the search, reversing transformation, applying them in the forward directions, expecting exactly how many products are formed. If there are more than one product formed, the transformation is actually marked as non-selective and assigned a penalty. Other algorithms are designed to identify motifs that are prone to side reaction arrangement. For example, Cynthia knows that an electron-rich, originally likely the alcohol substrate in the Prince cyclization may undergo a competitive oxonium prone to rearrangement will avoid proposing this reaction in the search. Even another molecule identify highly reactive groups that cannot be directed along for multiple steps, recognizing that. One prepared in organomagnesium species should be immediately used within the addition of aldehyde or ketone. And if it's not feasible to make it, and then try to perform other reaction on other parts of the molecule stay intact. So this allows Cynthia eliminate the sequence of the step in which label or highly reactive group are present for more than one step in the synthesis. Finally, Cynthia contains a list of non-existence and particularly stranded motif which is applied for every molecule proposed within a pathway. And if any symptom contain one of these motifs, is eliminated from the further consideration. In 2016, approximately 50,000 expert hand-coded rules with the algorithm was built up. It was able to recognize chemical logic. Cynthia was subject to very first real test to find out whether the proposed route would be able to validate at bench. Up until that time, there was no proof that you could utilize the software to plan a synthetic route for non-trivial molecules. There could be successfully executed in bench until we engaged in experiment in collaboration with Professor Bato's team, who is creator of Cynthia. The 7 target molecules, as you see in the screen, have high financial interest, and those were suffering from low yield and high cost. And one particular molecule has not been published in the literature. It was kind of the novel molecules. So we took these molecules and traveled to Poland to meet Professor Bato's teams and to learn how to use software so we could start planning the pathway for these molecules. Throughout the course of the searching, we kept in mind that we wanted to mimic the everyday pressure of chemists may be under. So we choose the route with commercially available building block in stock and ready to ship because we only had 8 weeks to whether it's success or failure. We also avoided the reactions that are not feasible from a safety standpoint. The important rules was that no route were allowed to be modified in terms of substituent step. Actually, the software was planning as well. So we expected only 50% of the success rate, but we were able to accomplish 100% by following the route exactly from Cynthia. So it was quite unprecedented result, and every route that was executed at bench was successful. So not only that, but also significant cost and yield saving were achieved in the process. So even for novel molecules having never been synthesized before in the literature was clearly demonstrated with Cynthia. So up until that time, Cynthia had shown great promise with its capability, but it was still struggling with finding route to some complex molecule with no result, even when it knew all the individual reaction construct a viable synthetic pathway to target. Unfortunately, this program was unlikely to follow a series of steps if it did not provide structural simplification, but could lead to inefficient disconnection downstream. However, Cynthia showed remarkable improvement after the inclusion of algorithm that improve prediction of outcome of a reaction and prescribing exactly how to strategize over multiple steps. Another improvement made, and it was the expansion of a filtering software called it tactical combination. When synthesis of complex organic molecules is often not sufficient to gradually simplify the structure each lateral synthesis step. Instead, it may actually be beneficial to go through intermediate that does not produce any immediate gain and can even increase the structural complexity of intermediate, but such the theme for a step offering significant simplification. Tactical combination was formerly known as strategy. The first electrosynthetic step complexified the structure by introducing 5 membered rings but when you look at second step, show significant improvement of complexity. The tactical combination is very hard to identify, but can unlock new elegant synthetic approach. In early 2020, Professor Bato's team published the article, Computer-Driven Discovery of Large Number of These Two-Step Reaction Sequence of Tactical Combination, and it has approximately 4.85 million, the vast majority which have no previous literature precedent and had never been cataloged before. Up until this time, there was only 500 cataloged two-step reaction sequence. So here is one of the successful examples of validation of tactical combination. So up to this point, the shortest reported synthesis of imperanine had been 8 linear steps reported by Shattuck 2001. However, Cynthia had proposed previous unreported pathway that included the new tactical combination of strategies that had been discovered by computer. Cynthia's pathway are fully validated at bench, successfully give S imperanine with 27% overall yield, with 97% enantiometric excess. It's worthwhile to note that this pathway easily adjusts to use opposite enantiometric iridium catalyst in first step and to easily adopt it to synthesize unnatural R imperanine in 28% overall yield with 97% EE. With the successful implementation of tactical combination and validation, Cynthia complete additional strategic algorithm for elegant route with natural product, of which I will outline 3 important additions. The first is functional group interconversion, and that's 2 or 3 step sequence reactions which stabilized highly reactive functional group along synthetic pathway. Cynthia know about 100 functional group interconversion sequence like this based on the analysis of the several thousand classic total synthesis from the literature. The next is bypass. When the reaction you can offer significant structural simplification but cannot be applied due to presence of a cross-reactive functional group. Cynthia can use bypass algorithm. And this algorithm checks to see if the conflict removed by alternative reaction, and only then will apply this original simplifying transformation. Finally, you can also have simultaneous reaction. Algorithm are also implemented to combine reaction which can be performed on the same reaction as great example such as simultaneous reaction. For example, simultaneous deprotection of a benzoyl group from primary and secondary alcohol present here in Cynthia. The important thing is that all of these algorithms are connecting. So, for example, functional group interconversion sequence for simultaneous reaction can be a first step in bypass. This enables Cynthia to truly begin to strategize over multiple steps and suggest elegant and sometimes counterintuitive reaction sequence which were exclusively within the domain by human expert chemist mind. With the strategic thinking algorithm implemented, Cynthia now was able to rapidly and repeatedly identify the complex target, even natural product. So it was subject to toughest assessment whether or not the pathway design actually distinguishable by those designed by experts in the field. In order to obtain unbiased assessment, a Turing-like test was performed. 40 total syntheses were compiled, 20 from organic chemistry literature and 20 designed by Cynthia. The target chosen for Cynthia was similar complexity in terms of average mass and number of atom in stereocenter, and then bring as compared to those pulled out of the literature. Combining and randomizing the set of target, 18 synthetic experts in the field were asked to review in the score pathway on the likelihood that the pathway was designed by human versus machine. The result was quite exciting, and the expert reviewing and scoring this pathway, they could not actually able to discern their origin, whether Cynthia or human for natural product. So meaning to route designed by Cynthia were indistinguishable from those designed by human experts. In the publication, Professor Batos also validated 3 pathways, and one of these executed route was lamellodithine A, which is the challenging bridge polycycle links, as you can see. So this is the real screen of the Cynthia. It automatically planned it in Cynthia. We could find the pathway of lamellodithine A with the minimal adjustment of the default search condition. Yep, that is the screen of the Cynthia. So key element that Cynthia proposed the synthesis with the sequential construction of intermediate trying hydrobolation and Suzuki coupling and intramolecular Diels-Alder cycloaddition with provided access to degelded tetracycle bicyclooctane framework of lamellocidin, and then final hydrolysis to hemiacetal product. So Cynthia correctly predicted stereochemistry of Diels-Alder cycloduct and selective formation of thermodynamically more stable and less hindered stereoisomer in the last step. So finally, overall yield was 17.7%, and it was successfully executed. So this is what I prepared for you today. So hope I could deliver the information effectively. I know that 30 minutes are definitely short to cover all the information about innovative electrosynthesis software, Cynthia. So please request live demonstration of the Cynthia, so via this QR code, and then we will be reaching out to you quickly. So thank you for your time today. Thank you.